All right, let's get started. No quiz today. I had thought about doing one, but that means we're kind of due for a quiz here next week for sure. So today we are going to shift gears and start talking about these basic differentiation formulas. So up to this point, let's see, I'm recording, my microphone is on. All right. Up to this point, when we've been taking derivatives, it's required that we calculate a limit, right? That's what it's taken. And obviously, that can be complicated, right? If you went through all the homework for differentiation, you know what I mean. The algebra can be messy. But fortunately for us, there are a bunch of shortcut formulas for differentiation which completely eliminates our need to actually use a limit. So in calculus, you kind of have to suffer through the limits for a while with differentiation, and then at some point we put the limit away and we give you formulas, and that's what today is, all right? So there are a bunch, okay, and that's the notes for this section 2.3 is just a list of 10, 11 different formulas, all right? And so what I'd like to do is I'd like to go through these formulas and then just give you examples. The main idea, again, is that we no longer have to do the limit if we're asked to take a derivative. Aren't you all excited?
Sure.
All right. So let's look at the first one. The first rule says that if you try and take the derivative of a constant, you should get 0. Now I can illustrate this visually pretty easily. All right. So let me show you why this works. Let's say you have some function y equals f of x, which is some constant. So somebody give me a constant. 5. Okay, that's what I was thinking of. 5. Okay, so 5. This rule is saying that if you take the derivative of this, you should get 0, which means that the slope of the tangent line should be 0 everywhere. And if we graph the function, we go to 5, it's going to be a horizontal line, isn't it? And of course, if we pick any point and go up to the graph and say, what is the slope of the tangent line there? It's going to be parallel to the line, and the line has a slope of 0, right? So does it make sense without me proving anything else? Is that visually? Okay. So the derivative of all constants are just 0. Good? Let's move on. The next one. The derivative of x is 1. So let me do this one visually also. If I change this from a constant function to the function f of x equals x. Now, this is a very important function. You may recall that from college algebra as being the identity function. Do you remember that? It's called the identity function. The reason they call it the identity function is because what goes into the function is identical to what comes out. You plug in 2, it spits out 2. You plug in 3, it spits out 3. So this is the identity, and when we graph it, what does it look like? Like the diagonal? It's that perfect diagonal line. Do y'all remember where this came up? This also came up in college algebra. This diagonal was useful when you were trying to do something. Do you remember? Let's see, this diagonal. Okay, yeah, so this had to do with if you had a function and you were finding its inverse, the inverse function was a reflection over the identity. That's where it came up in college algebra. But just look at this function here. If we pick some value x, doesn't matter where it is, and we go up to any point, right? Doesn't matter where. What is the slope of the tangent line going to be? Well, it's going to be the same as the slope of that line, right? And the slope of this line is 1, right? Y equals mx plus b. Since this is a line, the slope would be 1, right? Does that make sense? So are we okay with just leaving it at that visually, that the derivative of x is 1? Okay? So far, I've been able to kind of hopefully convince you just visually that the first two rules are straightforward. Then we get to the power rule. Now this is a major rule right here. This one's harder to explain because this one says that if you have a function, y equals f of x, and that function is x to any power, okay? So now they're leaving that n as a variable. So that could be x squared, it could be x cubed, it could be x to the -1. It could be x to a fractional power, x to the 3/2. Doesn't matter what the power is. It's saying that the derivative of this is equal to n times x to the n minus 1. So let's just first understand what the formula says. To take the derivative of this power of x, you're going to drop the power down in front, right? And then you're going to subtract 1 from the power. And that answer is the derivative. It's that simple. So let me give you a specific example. As a specific example, if we have y equals, let's say, x to the 9th power, and we're asked to find the derivative, all we do is drop the 9 in front, rewrite x, and then subtract 1 from the power, and we get 8. And that's it. We're done. 9x to the 8th. Isn't that nice? Any questions on that? I'll explain. We're actually going to prove this rule. I'm not just going to give it to you. I can't give you this rule visually. The reason I can't give you this rule visually is because n can be anything, right? So there's an infinite number of graphs that we would have to look at, and we don't have time for an infinite number of graphs, right? So I need to do it a different way, which I will. Just hang tight. Let's try another example. What if we have y equals square root of x? Well, is that x to a power? Yeah, that's the same as x to the 1/2, right? And so if I take the derivative of this, let's see what happens. 1/2 drops out front. Then I have x, and this time I'm going to write it down. I'm going to take the 1/2 and subtract 1, right? And then 1/2 minus 1, if you have to do that on the side, you have to get a common denominator and make that 2/2. Turn the 1 into a 2/2. And then you do 1 minus 2 is -1 over the common denominator. You get -1/2. So 1/2 take away 1 is 1/2, -1/2. We are not going to use decimals here, so don't be like, this is -0.5. We want to use fractions all the time. So this should be 1/2 x to the -1/2. Are we clear? Now, do you remember that when you have negative exponents, that means you can drop it down to the denominator? Do you remember that? Like if I have x to the -2, that's the same as 1 over x squared, this property of exponents. Well, because I have a negative exponent here, I want you to realize that can also be written as 1 over 2x to the 1/2. So I have a fraction out front, right? 1 on top, 2 on bottom. So the 1 stays on top, the 2 is already on the bottom, but this x to the -1/2 drops down and joins the 2. Yes? And now, what is x to the 1/2 rewritten as a radical instead of as a fractional power? That's the root of x, right? So we could say that the derivative of the square root of x is 1 over 2 root x, right? Now this one comes up a lot, right, Diego? This one comes up a lot. So put a star next to this one, because I would suggest that from here on out, if you ever see root x and you're asked to take the derivative, you need to just memorize that it's 1 over 2 root x. 1 over 2 root x. Instead of going through all this stuff. This one, I don't think you need, this is not a memorization thing because the number's nice, right? Just drop the 9. But this one comes up so much that you should just put it in here. All right, let's do another one. I'm going to still prove the rule to you, but I just want to practice a couple of these. What about this one? What about y is equal to 1 over x to the 4th power? So what is the derivative of this? Well, One part of you might think that what you can do is just do the top and bottom separately, like take the derivative of 1 and then take the derivative of this and write the answer down. But that is incorrect. All right? We right now do not have a way of taking a derivative of a fraction. I haven't told you how you can do that. I've only told you how you can do the derivative of a constant by itself, right? You don't have a constant by itself. You can take derivative of x by itself. You don't have x by itself. Or you can take derivative of x to a power. So the question is, can you rewrite the original equation as x to a power? Okay, what would it be? X to what power? X to the negative 4. So first I rewrite it, and then I apply this rule. So what's gonna happen here? Negative 4 is going to drop out front. X to the, you're going to go negative 4 and take away 1. So be real careful there. Negative 5. Right? Negative 5. So you're going to have negative 4 times x to the negative 5. And then you're going to drop that x to negative 5 down, and it becomes negative 4 over x to the 5th. We'll do one more. How about 1 over the cube root of x squared? All right, so you first have to try and rewrite that as x to a power. So I'm gonna first realize that this is 1 over x to what power? Which one is it? Is it 2/3 or 3/2? It's 2 over 3. All right, so if you need some clarification, this is a property of exponents from college algebra, that if you have the nth root of x raised to the m power, that is equivalent to x raised to the m over n. So this is how we converted from what we call radical notation to rational exponents. So you need to be comfortable going from this to this and from this back to this. We okay with that? All right, so that's raised to the 2/3. And now it's still not x to a power. It's 1 over x to a power. So how can I rewrite this? X to the negative 2/3. Okay, now I'm ready for the derivative. So my negative 2/3 is going to drop out in front. X to the negative 2/3, and then I'm going to subtract 1. And for that, I'm going to just do that real quick, that arithmetic. When I do this, then I need a common denominator, so I'm going to rewrite the 1 as what? 3 over 3. And just be careful here, you're taking negative 2, you're subtracting 3, which gives you negative 5 over 3. So negative 5/3. And trust me, when I was a Cal 1 student, I was not comfortable with doing negative 2/3 minus 1 in my head. Okay, I needed to actually do that. All right, so, but as you do more and more of this, as you're forced to do this, you're going to get better and better at doing this in your head. It's just going to come with time. All right. So this is going to be negative 2/3 x to the negative 5/3. All right, let's keep going. This is the same as negative 2 over 3 x to the positive 5/3, isn't it? So dropping this down. And then this, let's rewrite this in radical notation. And I'll do that over here. What is that in radical notation? So negative 2 over 3, and then the cube root of x to the 5th power. And we can actually go even further, because the number in here is bigger than the number out here. So let me try and illustrate what I mean. We can take something out, but let's see what we can take out. So just on the side here, cube root, that's x to the 5th, right? So that's x. times x times x times x times x. That's x to the fifth, right? And because we're doing a cube root, we're looking for groups of 3. So if we see a group of 3 in here, that's x cubed. We can take the cube root of x cubed, and that's just going to be a single x. So we can like almost look at it as pulling an x out. Is that fair? Or okay, this is college algebra stuff. So this is going to be x on the outside. I still have cube root, and then I had 2 x's left over, right? So I'm going to put x squared here. So this, be careful, that's not x cubed, right? This is x times the cube root of x squared. So that's what this is. Negative 2 over 3x cube root of x squared. All right. Now, you ready for me to prove to you why this formula is this? I'm going to prove this to you now. So buckle up. All right, before I can prove that to you, I need to establish a few things. All right? So, see how I want to do this. All right, let me erase this. I need some space for this. All right, what I'm going to do over here is I'm going to write something down here. Let's use x plus h. X plus h. I'm going to take x plus h. If this seems like weird, like why am I doing this? Like where is this coming from? Just be patient. If I take x plus h and I raise it to the 0 power, what do I get? So anything raised to the 0 should be 1. All right, I'm going to put that 1 right here. Okay, now I'm going to do x plus h to the first power. So what happens if I do x plus h to the first power? I get x plus h. I'm going to write it like this. All right? And then what happens if I do x plus h squared? I get x squared plus 2xh plus h squared, right? So that's, if you multiplied the two together, that's what you would get. Yeah? Okay, now let's do x plus h cubed. So you may or may not have that one memorized. A lot of people have this one memorized because you've done it so many times. This one's going to be x cubed plus 3x squared h plus 3xh squared plus h cubed. That's that one, okay? You're just going to have to trust me on this, all right? That if you took x plus h times x plus h, multiply it 3 times and collected like terms, you'd get this, all right? These are called binomial expansions. These are binomials, and we're expanding them out, right? So let's take a look at the next one. X plus h to the fourth is going to be x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh to the third plus h to the fourth. So again, take it on faith that that's what it is. Okay? Now, I'm trying to establish a pattern right now. X plus h to the fifth. X to the fifth plus 5x to the fourth h plus 10x cubed h squared plus another 10 x squared h cubed plus 5xh to the fourth plus h to the fifth. All right, this is starting to look like a mess. All right, so I obviously, well, I don't, maybe it's not obvious, but I don't have these memorized, okay? I'm not just sitting up here spieling these off because I haven't memorized. I know what the pattern is. Okay, there's a pattern in this. So let's talk about the pattern. First of all, I want you to look at just the x's, all right? In the first line, how many x's do we have? None, okay? In the second line, we have x to the first power, and then x to the, there's no x here, x to the 0 power. Here we have x squared, then what happens? Just x, and then no x. X cubed, x squared, x, no x. So can you see that the powers on x are coming down each time? And notice that the first power, right, the fourth, third, second, first, and 0 correspond with these numbers up here. Yes? Okay. So given that information, x plus h to the sixth, if I just write the x's down, what should I have first? X to the sixth, and then I'm going to have plus, and I'm going to have something here, but x to the what? Fifth, and then plus something again, and I'll have x to the fourth, and then plus something again, and I'll have x cubed, and then eventually I'll have an x squared, and then eventually an x, and then eventually I won't have any x's, right? That's the pattern. Now let's look at the h's. How many h's do I have here? None. Then here, look, we're going to move from left to right. I have no h's, then one h. No h's, an h, then an h squared. No h's, an h, h squared, h cubed. So aren't the h's doing the opposite of what the x's did? Instead of the powers coming down, the powers are going to go up. So I should have no h's here. Then what? Just a single h here. H squared here. H cubed here. H to the fourth here. H to the fifth here. And the last one should be h to the sixth. And again, that number, that highest number, matches up with this, right? The only thing left is to figure out what we call the coefficients, which are the numbers in front. These numbers. Because those numbers don't appear to follow any pattern, not initially. They don't initially look like they have a pattern. So what I'm referring to is the numbers in front. These coefficients. We have what? Like 3, 2, 3. There's a 1 there. We've got 1. We got 4, 6, 4, 1. Do y'all see these? Okay, so to get those numbers, what we can do is, and I'm going to have to squeeze it in here if I'm going to get it on camera, is we can develop something called Pascal's triangle. So if I start out, and let me write down just the numbers without the x's and h's. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. All right, so notice something about these numbers. The first row has one number, the second has 3, third has, sorry, did I say the second has 3? First one has 1, second one has 2, third one has 3, fourth, right? So as we move down, you get one more number each time. Now let's see how these numbers are developed. All of the outside numbers on this triangle are 1s, right? So I should have a pretty good guess right now that this number right here should be a 1 and this number right here should be a 1, right? Okay, so I know that maybe this one's 1 and the next one over here is 1. All right, let's see. How did we get, we had 1, 1 here, right? Well, if we're following the rule that the two ends have to be 1, then the second row follows our pattern, right? But the third row is where something different happens. My two ends are 1, aren't they? But where does that 2 come from?
You add the top two numbers and then they give the middle number.
So this number right here comes from adding these two together, adding them. So when I take 1 plus 1, I get 2, right? Yes? Now, that gets us our 2. Now, how do I get the 3 here?
You add the 1 plus 2.
I add the ones above it, like this. 1 and 2 gives me 3. How did I get this 3? This 2 and this 1, right? How did I get this 4? The 1 and the 3. How did I get the 6? The 3 and the 3. Understand? 4 comes from 3 and 1. This 5 comes from 1 and 4. The 10 comes from 4 and 6. The 10 comes from 6 and 4. The 5 comes from 4 and 1. Got it? Sure? Okay, so what would be my next number in this sixth row? 6 here. 15. 20. 15. 6. And then the 1. So those are my coefficients. Hold on just a second. 6, 15, 20, 15, 6, and 1. Yes?
I also noticed that it like doubles every time it goes to like the next row. Like the total
What doubles?
Like the total amount of numbers like doubles. Like it just goes.
Like if you add them up?
Yeah.
There are so many. This thing called Pascal's triangle. Just go Google it sometime, okay? Pascal's triangle. There are a bunch of different patterns in Pascal's triangle. There's so many of them. I don't even know. You can get these numbers by adding the previous two, but you can look at things like, okay, just take the sum of the row and look at the sum, and there's some pattern in that. There's just a bunch of different patterns. So I'm not going to get into a bunch of them, but yeah, you could check that yourself. Add them up, see what happens. All right, I'll just add a little side note to this. Pascal was a mathematician. We call this Pascal's triangle, but the Chinese actually had discovered this long, long before Pascal did. For some reason, he gets the credit for it. But okay, all right. Now, somehow, some way, this is going to help us get the power rule. All right, somehow, some way. So what I'd like for us to consider is this: could you get the next row? Could you get x plus h to the 7th?
Yes.
Yes? Okay, I believe that you could. Let's talk through it. I don't want to write it down because I need room here. What would our first term be? X to the 7th. Okay, what would the next term be? 7. That comes from the 1 and the 6. So 7x to the 6th h. We're going to have that h show up now, right? What would the next one be? Well, here, let's get the numbers. Let's get the numbers over here. What our two n's are 1 and 1, right? Then we would have what? 7, 21, 35, 35 again, right? Because look, 1 and 6, 6 and 15, 20 and 15, 20 and 15, then 21 again, and then 7. So those will be our coefficients. And then it'll be, what, like x to the 7th, 7x to the 6th h, plus 21x to the 5th h squared, plus 35x cubed h cubed, plus, am I off there?
X fourth.
Okay, I have to write down. You get the idea, right? You get the idea of how you could fill this out? So you can go impress your friends if you'd like. You can start drawing this out, be like, yeah, I know all these. Okay, so now, my question is this. What would happen if I had x plus h to the n? This is going to be tough. Okay, tell me about the first term. X to the n. All right, and there's a 1 in front of it. X to the n. Okay. Now, I want you to focus all of your attention on the second terms for all of these. The second terms right here. I'll just go, well, that's the second term there. I want you to focus your attention on those second terms. What can you tell me about the number that's here? So I'm trying to say plus, there's some number. What about this number? This 6 matches the exponent. The 5 matches the exponent. The 4 matches the exponent. Do you see that?
Yeah.
Okay, so I could assume here that my next term is going to be what? N. And then tell me about the power on x. It's got to come down by 1, right? It's got to come down by 1. So x to the n minus 1. And then tell me about the h. Do I have an h there?
Yeah.
Yes, it should show up. So I have one h there. Yes? Okay. Now, the rest of this, I'm going to concede that I'm not going to be able to get it. All right? But just let's make sure everyone's on the same page. Everyone clear on how I got that?
Yes.
Everyone clear on how I got that? Doesn't that look pretty damn close to the power rule right there?
Yeah.
Okay. The rest of this, I don't know the coefficient, okay? I don't care to know it. I am going to have x to a power here, right? So I'm going to actually have x to the n minus 2 because the power is going to come down again. But now I'm going to have h squared. And then, again, I'm going to not care about the coefficient. I'm going to have x to a power. Actually, I don't care about that power either. And this is going to be h to the 3rd, right? H to the 3rd. And then I'm just going to have a bunch of crap in here, right?
Yeah.
And then it's going to stop eventually where?
X to 0.
X is going to be gone. Coefficient's going to be 1. And I'm going to have h to the what? N power. Okay, do y'all agree with that?
Yes.
Sure? Got it? All right, I'm ready to prove the power rule now. Don't forget that formula. Actually, I'll leave it down there. I think I can leave it there and do the proof up here. So the only way I can prove this to you is by going back and using the limit definition. That's the only way that I can legitimately prove that this formula is correct. So here's what I'm going to do. I'm going to start out, I'm going to let y equal x to the n. And then I'm going to find y prime. And to do that, I'm going to take the limit as h goes to 0. Remember the formula? Let's call this f of x, okay?
Yeah.
Let's call it f of x. So it's f of x. We're going to, instead of using a, I'm going to use x, okay? So I'm going to be doing limit f of x plus h minus f of x all over h. That fair? Now this is equal to limit h goes to 0. Now let's plug x plus h into the function. That means plug it in right there. So isn't that x plus h to the n? Ah, isn't that x plus h to the n? Okay, and then minus what? F of x. What is f of x? X to the n. All over h. We still good? All right, now watch this. This is awesome. Okay, this equals the limit as h goes to 0. Now what is x plus h raised to the n? It's all this. Okay, so I'm going to write that down. It's x to the n plus n times x to the n minus 1 times h plus something, I don't really know what it is, x to the n minus 2h squared, right? Plus something, and then there's another x to a power, I don't care, h cubed plus, and then it's just a bunch of crap, and at the very end of it, I have h to the n. So that's this rewritten right there, right? Then what? Minus x to the n. And all of this over h, yes? Now what we were hoping for is for good things to happen algebraically so that we could cancel an h, right? And it's going to happen. Look at your x to the n's. This guy right here and this guy right here are gone, aren't they? Now what can you tell me about everything that's left up here? They all have something in common. They all have an h. They all have at least one, right? This one has 1. This one has 2 h's. This one has 3 h's. And every single one of these has h's in it, all the way to h to the n. So can't I factor a single h out? Mm-hmm. Let me do that. I hate this dot in the middle of the board. Okay, this is equal to the limit as h goes to 0. I'm pulling an h out. And when I pull an h out of this, what am I left with? N x to the n minus 1. And there's no h there with it anymore, right? And then plus this junk, x to the n minus 2. And didn't I pull one h out? But I still have one h. And then plus, now look at the rest of these. Okay, this is the most critical part. The rest of these, as I start pulling h's out, I still have h's there, don't I? Mm-hmm. So the next term is going to have h to some power in it, plus the next one, is going to have h to some power in it. Those are question marks. And then at the very end, I have h to the n minus 1. That was this guy right here. I pulled one h away. I had this. Yes? Mm-hmm. All of this over h. These h's cancel. Now, let h go to 0. Take the limit, let h go to 0, and the fact that this has an h in it, and this has an h in it, and this has an h in it, everything down here has an h in it, these all go away. And the only thing you're left with is that first little piece right there, which is the power rule.
My God.
That's pretty neat, huh? That's how you prove the power rule. Now, you don't need to prove it, you just need to use it, be able to use it.
So that's
right?
any
Power, any exponent, yes. Yep, there was no condition in this that n had to be any, like, integer power or anything like that. All right, so we got the power rule out of the way. That is a major one, all right? You've got to be comfortable with that one. All right, the next one is what we call the constant multiple rule.
Is there the linearity property?
Of what? Yes. Uh-huh.
This is still
2.2, right?
2.3. 2.3. All right, so look at this one. This one says, this is a little bit weird the way it's written up there, but it says, look, you're going to take the derivative of something, and it's a constant times a function. Okay, that's multiplication right there. Then it says that what you can do is you can take the constant and multiply it times the derivative of the function. Okay, what? All right, so let me give you an example. Let's say we have y equals 5x to the 7th, and we want to take its derivative. You see 5 is attached to x to the 7th through multiplication, right? Now, the derivative of 5 by itself is what? 0. But if that 5 is attached to a function of x, you do not say the derivative of 5 is 0. What this property says is that the constant is just going to sit out front, and you're going to take the derivative of the function part. So in other words, I'm going to just bring the constant along for the ride. Here it is. There's my 5. It's going to come with me, and then I'm just going to take the derivative of that. And that's power rule. So 7x to the 6th power. And then you can multiply these. 5 times 7, 35. X to the 6th. And we're done. The thing you have to be careful with this constant multiple rule is that if it's a constant by itself, derivative 0. But if that constant's attached to a function, the derivative isn't 0. It just comes along. All right? Give you another one. What about this one? Y equals 1/2 x squared. What's the derivative here? So that 1/2 is attached with multiplication. So it's just going to come along. And then derivative of x squared, 2x, right? And half of 2 is 1. So this is just x, isn't it? So it's almost like you could say the 2 came out, and you can do this. You can actually multiply 2 times 1/2 right off. You don't have to write this down. You can go straight from here to here. I don't think I'll prove that one. That one, unless you'll want it. No, I want more time for other proofs. Okay. All right, the sum and difference formula. This rule says, again, it looks complicated, all right? But all it's saying is that if you have two functions that are being added or subtracted, sum and difference, right? If they're being added or subtracted and you're trying to take the derivative, so I'm trying to take the derivative of two functions that are being added or subtracted, that I'm allowed to actually split them up and do the derivatives separately. Only if you have addition and subtraction, though. So an example of this would be, let's say y is equal to 4x to the 3rd minus, let's say, 5x squared. So now that, do you see that our functions are becoming a little more complicated? Like my first example, I don't remember what it was, like x to the 7th or something like that. It was very simple, but now we're starting to add some complexity to it. We've got numbers in front, and we've got two pieces. So according to the rule, I'm allowed to do these individually, right? So what would the derivative of that first one be? Well, hold on, don't say it. Don't say it. I want to just call on people randomly today. I've been doing this in my other classes, and I kind of enjoy it. So I'm going to have my phone generate a random number. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ryan, where's Ryan? All right, Ryan, you're up. So look, there's no shame in being wrong here, okay? I'd rather you be incorrect today than to be incorrect on a test. So I just want to see where you are comfort level-wise. Ryan, what do you think?
So it would be 4 times 3x squared.
Okay, so you're going to go through it. 4 times 3x squared. Go ahead. 5 times 2x. And then when you clean that up, that's just going to be
12x squared.
Minus 10x. That's it. You probably would like to see your next test have about 30 of those, right? And then we just call that a test. So there's There's good news and bad news today. The good news is that these rules make life a lot easier in terms of calculating limits. That's great news. The bad news is that because it's easier, now our functions can become more complicated. All right, so we can deal with functions that we've never seen before, like, I don't know, like that function. Like you've never seen that function before. You've seen square root by itself, you've seen sine by itself, maybe you've seen sine squared, but maybe not. But this is actually this function times this function. And we could graph it. And the question would be, what's the slope of the tangent line at certain points? Well, you're going to need to be able to take the derivative. Well, how do you take derivative of that, right? Well, that's why we have these rules. So it's kind of, be careful what you wish for. Like, yay, we got the rules, but now the functions get harder. Okay, so I think that's good with that example. That all right with you? Okay, let's move on. All right, common derivatives that you just need to know. The derivative of some of the trig functions. In fact, I have all of them here. So you remember your trig functions from pre-cal, right? There were 6 of them, sine, cosine, tangent. And then all the reciprocal functions. You had cosecant, secant, cotangent, right? Well, here are their derivatives. So here's what I'm going to do. I'm going to do the first one, all right? I want to show you this one. I'm going to prove that the derivative of sine is cosine, and I'm going to do it 2 different ways. I'm going to do it visually, and then I'm going to do it using the limit. All right? So let's do this. I'm going to try and convince you that the derivative of sine is cosine. So let's take a look at the graph of sine first. If I asked you to graph sine, just one period of it, you would start here, you would end here at 2 pi, halfway would be pi, then you have pi over 2, this is 3 pi over 2, and then you have amplitude would be 1, so you're going to go up to 1, back down, then back through, and then like that, right? That looked like the good old sine function from pre-cal? All right. Now, let's talk about its derivative. I'm going to leave this right here. Let's talk about its derivative. So I'm going to try and graph its derivative. Remember last class I gave you a function, asked you to graph its derivative? Right? So the purple one here is Sine X. Okay, some important places. Can you tell where the derivative is 0? Right? The derivative is 0 at pi over 2. It doesn't look like it, but there and 3 pi over 2. So if I graph the derivative, I should have 0 here and 0 here. Yes? Agreed? All right. What would if I start at this point and let's say I move to the left, what would that slope of that tangent line be? Right here, it's going to be what? Positive? So it's going to be small positive, and it's going to get a little bit steeper, right, until it gets to about here. Yes? And that looks like a slope, I don't know, maybe of about 1. It is 1, but so what happens is I draw the derivative, I'm going to have small positive numbers that get closer to 1. So I'm going to do something like this, closer to 1. See that? Now what happens is I move to the right of that point. I'm going to have small negative numbers until I get to here. That's -1, slope of -1. And then what starts happening here? It starts to straighten out, right? And so my pitch is still negative, but they're smaller negative numbers. So that means I have to go small negative numbers until I get down to -1. Then I'm still going to be negative, but I'm going to be getting closer to 0 until I get back to here. So there, slope's 0, function is 0, derivative is 0. And then once I go to the right of this, small positive until I get to a slope of 1 again. So small positive until I get a slope of 1. And that's your cosine. That's cosine x. So amazingly, the derivative of sine is cosine. The derivative of sine is what? Cosine. All right. Let's try and do it algebraically. That's just a visual. That's not a proof. That's just to kind of help convince you that maybe it's true. But if I truly wanted to do it, what I would do is I would let f of x equal sine x. Then what I would do is I would try and find f prime of x which would require me doing the limit as h goes to 0 of f of x plus h minus f of x all over h, which for us would be the limit as h goes to 0. Now what is it? What happens when I plug x plus h into this function? What do I get? Sine of x plus h. And then minus f of x, which is sine of x, all over h. That's the setup, right? That's what it would look like. Now, unfortunately for us at this point, we don't have an easy way of doing anything algebraically. If we let h go to 0, this goes away, we get sine x minus sine x, which is 0, and then we have division by 0. So we know we have 0 over 0, but what algebra is going to be necessary? We can't, like you can't just split sine that into sine x plus sine h, right? Like sine doesn't split that way. You can't distribute sine through. I heard conjugate maybe, but even if we do the conjugate, the reason the conjugate's great is it's very useful when we have roots because it kills off roots. Instead, I'm going to do this. And let's just see if you agree with this or not. All right, does anyone know what I just did? I split this up. I actually did use something to go from here to here. This right here is this. This, if you go back to pre-cal, was we had a sum and difference formula for trig functions in pre-cal. We had something like sine of x plus y equals, and then it was something, and then we had, if it was a minus, it was something else, and then we had the same things for cosine, didn't we?
Yeah.
So does that look familiar? Yeah. If you have your formula sheets that you can have on the test for this class, that you get off Canvas, that you can print out, that formula should be on there. But that's a sum formula for sine. Y'all okay? Can I continue? Now, by doing that, something really kind of amazing happens. What I can do is I can take the limit here as h goes to 0, and let me see. Let me rewrite this. This is the same as sine x cosine h minus sine x, sine x, yeah. Sine x over h, and then plus sine h cosine x over h. Now, let me try and explain what I just did there. Every single one of these terms, this one, and this one, are all divided by h, right? Mm-hmm. So I could split that into 3 separate fractions if I wanted to, couldn't I? I could do this over h, this over h, this over h. What I've chosen to do is take this over h, okay, and separate it, pull it out, and put it right here. And then I put these two together over h. Is that all like fair legal algebra for you? Okay, so I just kind of rearranged things, but I did it for a reason. You'll see the reason right now. This is equal to the limit as h goes to 0. I would never expect that you would do this, okay? Like that you would just be sitting there and go, oh yeah, I'm going to do the sum formula and come up and then rearrange. I'm showing you this because someone else had to grind through this and figure it out, all right? We just get to appreciate that they did it for us, all right? So I'm going to take this here, and I noticed that they both have sine x, don't they? So I'm going to factor sine x out. And then when I factor that sine x out completely out of this, I'm left with cosine h minus 1 over h. Okay, that's this first one with the sine x pulled out. Over here, I'm not really going to, I'm going to pull something out, but it's really not pulling anything out. I'm just going to write the cosine x out front and write sine h over h next to it. Okay, do you agree that this is the same as this? Yep. All right, we're there. Because I'm now going to let h go to 0. And I hope you recognize that. What is that? That goes to 1, right? That's sine of junk over junk. They match exactly, and they both go to 0. So that was that important limit that I said you needed to memorize, that this goes to 1. Okay? So when I take the limit, this goes to 1 times, now look, cosine x doesn't have an h in it, right?
Yeah.
So h going to 0 has no impact on cosine x. So this is still just cosine x. All right? I have the plus in front of it. Now, this one was, I gave you in your notes 2 important formulas to remember. This one and that one. This one we didn't use as much, but that one goes to 0. Okay, so this one goes to 0, and in front of it is sine x, but that's not going to matter, is it? Because 0 times 0 is gone. So all you're left with is what? Cosine x. So the derivative of sine x is cosine x. Now you could do a similar setup, and you could even do the limit to show the derivative of cosine. So derivative of sine of x is cosine x. What is the derivative of cosine x then? It would be nice if it was sine x, wouldn't it? But it's not quite sine x. I think I'll do it visually. I'm not going to do the limit. Okay, is that all right if I don't do the limit on this one? You would do it exactly the same, except when you did that part using the identity from pre-cal, it would be the sum formula for cosine instead of the sum formula for sine. All right, so for this one, I'm going to try and visually convince you that the derivative of cosine of x is negative sine x. So here's cosine x. All right, that's cosine x. If we were to look at the important points here, we would have here our derivative would be 0, here our derivative would be 0, and here our derivative would be 0. So that means if I graph the derivative, I would have those x-intercepts. That already is starting to look like sine, right? Because sine, it's just a matter of, let's connect these pieces. So what happens to the slope of my tangent line as I move to the right here? Is it positive or negative? Small negative, right? And then it gets to -1, and then it goes back to 0. So it's small negative, gets to -1, right about here gets to -1, then it goes back up to 0. And then once you get here, we have small positives until you get a slope of 1, and then back to 0. So it's going to go small positives up to 1, and then back to 0. And that is not sine. That's sine flipped over. So that's negative sine. Those have to be memorized. Derivative of sine of x is cosine x. Derivative of cosine x is sine x. And then the next one has to be memorized. Tangent. The derivative of tangent to x is secant squared x. Now this one I will prove to you, all right, but not yet. Just for now, try and remember it. And then you have the rest of them. Derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x tangent x, and the derivative of cotangent x is negative cosecant squared x. Yes, okay. I haven't used those in a while, so there we go. I don't care so much that you memorize these right now as I want you to memorize the ones for sine, cosine, and tangent. But definitely when you get to calculus 2, the more you can remember these, the easier it's going to be to do what you need to do in Cal 2. All right. Feeling all right? I'm going to give you a couple of problems to do here, all right? And this isn't going to be turned in or anything. I just want you to work them out. And you know what? I'll pull some problems from the book that are similar to what's in the book. And we'll spend about maybe 10 minutes working on these, and then we're going to move on. All right, so an example here. Let's say that you have y equals x to the 5/3 minus x to the 2/3. So I want you to find y prime. Next example. F of x equals the square root of 3 times x and then plus the square root of 3x. Now these are a little challenging, all right, because they're not going to be like exact cookie cutter problems from what I did today. You're going to have to think a little bit about these. Do y'all see the difference between these two expressions? Here, the x is not under the root. Here, the x is under the root. All right. And then, how about one more? Let's use some different variables. How about g of u equals pi tangent of u. All right, you may speak to one another. I'll give you a few minutes to see how you do here. What's that?
A quiz question.
A good quiz question?
Yeah.
Oh, what?
So, I take the constant. Just have to use power rule. So what I mean by that is like say we have 5, right?
Mm-hmm.
So the summation of 5x to the 0.
Mm-hmm.
If you were to use power rule, you would get
Mm-hmm.
doesn't matter what the value of that is because it's just going to end up, that 0 is just going to end up multiplying by it.
Yeah,
That's not obvious.
I'm not sure. You're saying give this as a quiz? What?
Maybe give it as like a conceptual question.
Like use the power rule to do this problem? Is that what you're saying? Okay, I know what you're saying. You're mean.
Is that x inside of the root?
This x is inside the root.
No.
This one is not. I'm going to start putting answers up here. So if you don't want the answers, just don't look up here, all right?
I got a review.
I'm going to leave it as negative exponents for now. Yeah, that's fine. You just should be comfortable if you needed to, like if you were trying to match your answer to the back of the book, you're going to need to do some additional simplification. I just wanted to throw kind of the raw derivative up there.
Try to know.
Okay. If you have any questions, you can raise your hand. I don't mind coming by and helping you.